Okay, can you see the screen?
Yes.
Yes, sir.
All right. Okay. Okay, so let's start with this first question. Question number one. The mean value of an alternating current is 0. Does everyone agrees with that? Is it understandable why this statement must be true? Yes?
Yes.
Is it? Okay. So basically, an alternating current flows like this, right? So the mean value of this lies at this axis where the current is equal to 0. Just give me a second. Yeah, okay. So the mean value of alternating current is 0. Explain why an alternating current gives rise to heating effect in a resistor. So heating effect in a resistor if I have it connected to an supply of an alternating current. Okay, so heating effect is related to the power. The higher the power there is, the higher the power loss or power dissipation happens, the greater the heating effect is. And what do we know about power in terms of current? We know that power is equal to the power dissipated across a resistor is equal to I squared R, where I is the current. In this case, it would be the alternating current. So what happens is, if I take the square of this value, doesn't matter if the current is negative in this regime and positive in this region. If I take a square, if I square it, then the value of alternating current is going to be positive. And which means that the power itself would also be a positive power. And if there is some positive power loss or positive power dissipation in the resistor, that would mean that there is some heating effect being produced. Is that clear?
Yes.
Okay, so it is the heating effect is related to power, which implies that power is proportional to the square of current. And so square of alternating current will be positive, which implies that this would cause a heating effect in the resistor. So the resistor would heat up slightly. Okay, now by reference to this heating effect, what is meant by the root mean square value of an alternating current? What do you think? What first of all, what do you generally mean by a root mean squared value of an alternating current? So when we find this value r.m.s, which is what, by the way? It is equal to the total current divided by square root 2. So what do you mean by root mean squared value of an alternating current? What does that statement physically implies in a circuit? If I'm using this value of current, root mean squared value of current. Anyone? Okay, so remember when we were doing our lecture, we saw that this root mean squared value of an alternating current is it is the value of the direct current that I can use. If I'm using a direct current circuit, I can use this particular value of the direct current, and it will cause the same energy transfer rate of energy transfer, or you can say power dissipation, as an alternating current would have caused, right? So in a way, roughly, loosely speaking, you can say that it is the value of the direct current that would be an identical, that would cause an identical effect if it were an alternating current, right? Now, first of all, is that clear?
Yes.
So in this case, if I use the reference of heating effect, what can I say about this thing? It's so again, the definition was that it's going to cause a same energy, a rate of energy transfer, a rate of energy loss across a resistor as if it were an alternating current. And that rate of energy loss or energy dissipated at per unit time is just power, which is what? Just the heating effect. So what you can say is that it is the value of direct current that would produce the same heating effect as AC in a resistor, right? Because again, the heating effect is related to power, and power is just energy transferred per unit time. And so the value of DC direct current, I can use a value if I have a circuit like this. What does that mean? If I have a circuit and it's connected to a resistor like this, suppose this is just your circuit, and in this case there will be some I alternating current. I'll just call it IAC, and it's going to cause some of heating in this resistor. It's going to cause the resistor to heat up. Now what I can do is I can use a value of direct current. I can find the identical, you can say identical value of a DC current, identical in the case, in meaning that it's going to produce the same energy loss, and that value is the root mean squared value of the alternating current. And now if I use this DC, if I use a battery that is capable of supplying this current, I only allow this r.m.s to flow, then it's going to be identical. The resistor is going to operate identically as to this resistors. Okay, is that clear?
Yes, sir.
Okay, so okay, we can skip this question, but we'll do these parts where state the Faraday's law of electromagnetic induction, right? We can talk about this. So what is the Faraday's law of electromagnetic induction? You can just remember an equation for this electromagnetic induction, which states that the EMF induced in a coil is directly proportional to how fast the magnetic flux changes, minus d phi by dt. So change in the magnetic flux linkage. So you just have to write down this expression in words that would go something like it states that the induced EMF in a coil is directly proportional to the rate of change of magnetic flux. So if the magnetic flux changes, that would cause EMF to be induced, or in other words, you can say it would produce a current if the magnetic flux is changed, as we discussed it as well in detail. So that's clear, right? There's I don't think there would be any question from here. Let's go to the next page. Okay. So we're going to skip this one because transformers has been removed. So we don't need to talk about the primary coil and secondary coil. Next question states that the variation with time t of the output V of an alternating voltage supply of frequency 50 Hertz is shown. So we have an alternating voltage supply whose frequency is at a 50 Hertz. Use this figure 6.1 to state the time t1. Wait, where did I go? Yeah, actually, I'm going to lock this Zoom. So yeah, okay, perfect. So how can I determine this time t1 by using this figure? Any hints?
Can you repeat that?
Sorry, can you repeat?
No, I'm asking, can you repeat that?
Oh yeah, okay. So again, the question is that we want to use this graph, which is a graph of an alternating voltage supply, which has a frequency of 50 Hertz, which is already specified. We want to use this figure to state the time t1. This time t1. How can we
1 over
find
F.
the value of 1 over f? Exactly, because we know that frequency is 1 over time period. Now this would be t is equal to 1 over f, which is 1 over 50. This would be around about 0.03 seconds.
Sir, I
Yeah.
think there's like one full oscillation and then half.
Oh, you mean this one? So this is 1, and then there is a half. Okay. So what we can do is, so this time period is the time taken for one complete oscillation, right? So if that is the case, then this time period, 0.03, is just for one complete oscillation. But in our case, we have 1.5 oscillation. So that would be 0.03 times 1.5. So what does that give you? 0.045, which should be greater than the time period for one oscillation, right? So this time t1 will be 0.045. Okay, so it's clear. Is this thing understood?
Yes, sir.
Right. Okay. So now the peak value V naught of the voltage, again using this figure 6.1. How do we find that? What would be the peak value?
The amplitude.
The amplitude. So it would be the maximum value of the voltage, right? Which is this value. It is 15, 16, 17. So it's 17 volts. Okay. Next, the root mean squared value of voltage, v.r.m.s. So we have the peak voltage V naught as 17 volts. We know that root mean squared is equal to, how do you calculate the root mean squared voltage? The peak voltage divided by under root 2, which would be 17 volts divided by under root 2, which is just 12.0 volts. Okay, was that clear?
Yes.
Okay. So next, the mean voltage, this thing. If I look back at the graph, what do you expect? This is voltage and this is time. For this graph, what would you expect the mean voltage to be? So we have discussed this in a previous question as well. What should be the mean average voltage of this alternating supply? Anyone? Just take a guess if you're not sure.
0.
It should be 0, right? Exactly. Because again, if the in this case we have plus 17 and here we have minus 17. So if I take the average of this, it would be 0. Or another way is that whatever is going up, whatever is up, there is an equal but opposite part of it down as well. Again, for whatever is up, there is an equal and opposite part of it down as well. This one. So always the mean value of the voltage of this type of an alternating current supply or voltage supply is going to be 0. So was that clear?
Yes, sir.
Okay. So now the alternating supply is connected in series with a resistor of resistance 2.4 ohms. Calculate the mean power dissipated in the resistor, the mean power. So this is the value that I am looking for. How do you calculate the mean power dissipated? So we know that power dissipated, or at least the maximum power that is dissipated, is I naught, the maximum current, times the peak current, times actually square this thing and times the value of the resistor. What about when we want to calculate the average power? Average power is given by taking the root mean squared value of the current, which is I r.m.s squared times R. Right? We derived this formula in the class as well. Now, what we want to compute in this case is the maximum current. So if you go over here, the peak voltage is 17 volts, right? So what I can do is I can say that I r.m.s is equal to I naught over under root 2, and the actually we cannot find this current, right? So let's use a different approach. Okay, so or we can do it. We can still do it. If I still use this thing that if I want this current, I can substitute it in terms of R, V and R, right? I know that V is equal to IR. I would be then just V over R. So I can say that this would be V r.m.s squared over R squared, right? Because it's I squared. So, and it's I r.m.s squared. So we will be using V r.m.s times R squared and then multiplied by R. So one of these R goes away like this, and we're left with V r.m.s squared over R. And we know V r.m.s was 12 volts and R is 2.4 ohms. So this would just, again, you have to square 12, and this would give you 60 watts. Is that clear?
Yes.
Yes, sir.
Okay. Next, the variation with time t of the current I in the resistor is shown. Again, the current I, we can see from the graph that this current is the alternating current. The variation of the current with time is sinusoidal. I don't know how you pronounce that, but whatever. It just means that it's a sine combination of either sine or cos wave. Explain why, although the current is not in one direction only, power is converted in the resistor. Why? It is the so what they're saying is that there will be some power loss, right? Power that would be converted in the resistor, as in, again, it is related to that problem we did on the heating effect, right? So they're saying that although there is alternating current, which is not in one direction only, it goes in two directions. So you would normally expect the average value to be 0. But this power does not depend on that. It depends on the square of the current. If it depends on the square of the current, what would be the graph of the square of the current? Let's draw it over here. So I have to square these values. So if this is starting from here, I square this thing, I get a higher value. So I'm going to plot it something like this. And then I go here, but now I'm going down. If I'm going down, I have negative values, right? But I'm squaring this thing. This is I squared. So this value will become positive. So it's not going to go down. It's going to go back up like this. And then again, this one, it's already up. So it's going to move up like this, which means that the power dissipated is going to be positive because the power depends on I squared, which means that it is independent of the direction of the current. So they talked in terms of the direction of the current. So you can say that the power converted depends upon the square of the current, or you can just say I squared, or if I'm saying square of, then I'll just write the entire word, square of the current, right? And remember, it's for 2 marks, and they have talked in terms of direction as well. So they're saying that although the current is not in one direction only, so they're giving some reference to the direction. So what we saw from this I squared graph is that this power is independent of the current direction, right? So which is independent of the direction of current. Was that clear?
Yes, sir.
Okay. All right. Using the relation between root mean squared value, r.m.s current, and peak current, deduce the value of this ratio, average power converted in the resistor to maximum power that is converted in the resistor. So first of all, let's write down the expressions for both of these powers. So the average power that is converted in a resistor is equal to r.m.s squared times R. And the maximum power, P max, is equal to the maximum current that flows, I naught, the peak current squared times R. Now, what do we know about I naught? We know that I naught is equal to under root 2 times IRMS. I can substitute this in this one, and I'll get under root 2 squared would be 2 and IRMS squared times R. Now I can take the ratio of these two. I'll see that if I take this ratio P max, I get, so this is I squared RMS, R divided by 2 times I squared RMS, R. I squared RMS will cancel, R and R will cancel. You're left with 1/2, 1 by 2, which is 0.5. So the ratio is 0.5. So half of the maximum power is converted in the resistor. Is that clear?
So can you explain this part again after the power max?
Okay, so from power max, we just use this equation I naught equals square root 2 times IRMS for I naught, right? And then you just substitute this back in this, so you get this thing. Now you want to find this ratio, right, that they're given you. So the average power to maximum power. Average power is I squared RMS. The root means squared value of the current times the resistor R. So that's what I wrote. Divided by, now let's write I naught in terms of IRMS, which was written over here. So you just put that value 2 I squared RMS times R, and these variables will cancel because there's the same upstairs and downstairs. We're left with 1 by 2. So the answer is 0.5. The ratio is half. Is that clear? Yeah. Okay. So I think there is one more question, but it is for transformers. So we can skip that. But we can do this at least. We can talk about this thing. Explain by reference to the direct current what is meant by the root mean squared value of the alternating current. Again, it's actually the same problem that we did earlier. You just have to describe the meaning of the root mean squared value of the alternating current. And what is it? It states that it is the value of direct current that would produce the same average power or heating effect in a resistor as alternating current, right? Alternating currents. Okay, so is that clear? Does everyone understand the meaning of root mean squared value of AC?
Yes,
Yes,
sir.
sir.
All right. So I think the meeting is going to end now. I was not aware of this, that the transformers have been removed, so I added some questions from transformers as well. So skip that, and there were not many more
Sir, can you
questions
send
for
this
alternating current,
worksheet?
but I hope whatever we,
Can you send this worksheet in the group?
yeah, I'll do it right now. Okay, so I'll leave the meeting. It's gonna end anyhow, just now. So I'll show you this.